In today's video, we're going to be talking about circular motion. After watching this video, you should be able to calculate the average speed of an object moving in circular motion, and then have just a general understanding of what speed, velocity, and acceleration are talking about for an object that is undergoing circular motion. So let's get right to it. Uniform circular motion is the motion of an object in a circle with a constant or uniform speed. So basically that means an object, a car, could be going around a racetrack at, 30 miles per hour. Okay, so it's going at a constant speed going around this racetrack. All right. The distance of one complete cycle around the perimeter of a circle is known as the circumference. Okay, so a little bit of math refreshing there. The circumference is basically if you were to take a walk around the whole outer portion of a circle, that would be the circumference. So an object with a speed of 3 meters per second could move around a circle with a circumference of 3 meters in 1 second. Okay, and this is one of those kind of like ratio unit things when we talk about speed. It's how many meters does an object cover in 1 second. Okay, so if I told you, well, this object could cover 10 meters in 1 second, basically it could go around a 10-meter track in 1 second. So just a little geometry refresher here. The circumference, the formula for circumference, that is 2 times pi, which is 3.14, times the radius. So if you want to calculate the circumference of a circle, you would just use this equation here, 2 times 3.14 times whatever the radius is. To calculate the average speed of an object going in circular motion, you take 2 times pi, which is 3.14, times the radius, so r is the radius, divided by the period. T stands for the period, and the period is just basically the amount of time it takes to complete one cycle or one circle or to go through one loop, if you will. Okay, so if it takes a car 10 seconds to travel around a track, well, that would be the period, is 10 seconds. Okay. Just some food for thought. I don't know if you guys have ever ridden on a merry-go-round before, but I'm going to draw like an above view of a merry-go-round, and here's the center of it. And let's say you have your friend kind of, pushing you around or making you whirl around in a counterclockwise direction. Where should you sit if you want to experience the most speed? Where should you sit if you want to experience the most speed? Well, I don't know if you guys can picture this, but if you sit way on the edge, you're really going to be whipping around this circle very quickly, all right? Whereas let's say you're maybe not such a daredevil and you want some speed but not a lot, you might sit more in the middle of the merry-go-round, like right here, okay? And let's say you just really don't want to spin at all, or very little, I should say. Where should you stand? Well, if you stood right at the middle, it takes a very long time for you to complete one rotation. Okay, so that's how this r is fitting into the equation. As r gets bigger, your speed gets bigger. There's a direct relationship between the distance you are from the center of a circle and the amount of speed you have. Okay, so if there's a threefold increase in the radius, so let's say that the radius is 3 times bigger, and the speed is then going to increase by 3 times. Okay, so kind of keep that in mind as you're thinking about problems. So we've been talking about that velocity is a vector, okay? And basically a vector is something that has a magnitude and a direction attached to it. When an object moves in a circle, its direction is constantly changing, okay? And kind of think about that. It's not like you're just going in a straight line. You're constantly changing your direction. The direction of the velocity vector at any instant is in the direction of a tangent line drawn to the circle at the object's location. Okay? And you may say, well, what the heck is a tangent line? A tangent line is a line that basically touches a circle at one point but does not intersect it. Okay, so let's just kind of like maybe a picture would help us understand this. If I draw a circle here, and let's say you're like right here, and this circle is spinning around counterclockwise. Let's say you stop holding on to the handlebars or the bars of the merry-go-round and you let go. What direction is your body going to fly? Well, at this moment, it is moving in this direction, right? That's a tangent line to the circle. You would fly that way, okay? Let's say you were standing here, and let's say you let go of the handlebars or whatever they're called. What direction would you move? Well, you'd keep going straight, right? This is just basically an example of inertia. You keep going in the direction that you were originally going, okay? So if you were here, where would you go? Well, you just keep going straight, all right? And if you were here, where would you go? Just keep going straight. All of these are tangent lines. It touches the circle at one point, but does not intersect it, okay? So there's no intersection going on. You would just fly off of that circle, okay? So this is why velocity is a vector. It has a direction and a speed associated with it, and basically the direction that you're traveling at the instant that you were to say let go of whatever it is that you're riding on, that you're going in a circle, would be the direction you would continue to travel. So for velocity to constantly change, there has to be an acceleration. Because remember, that's what acceleration is the very definition of, is that there is a change in velocity, whether it's speeding up, slowing down, or a directional change, okay? So here's a circle. And again, here are some the black lines are tangent lines, okay? So they're tangent to the circle. And the acceleration, you may say, well, what direction is the acceleration? The acceleration is always at a right angle to the velocity, okay? So believe it or not, when you're riding on a merry-go-round, you're always accelerating towards the center of the circle, okay? And this is a hard concept to wrap your mind around, but kind of just take my word for it, and we'll talk more about it in the next lesson. But the acceleration is always at a right angle to the velocity, and basically it's going to be moving you towards the center, all right? If the acceleration had any components in the same direction as the direction of the movement, okay, so the direction that you're actually traveling, you would either be slowing down or speeding up, okay? So remember, acceleration, it too is a vector, and basically it's going to have a magnitude and a direction. So for acceleration to exist here, it has a directional piece that's moving you towards the center of the circle, okay? You're accelerating towards the center of the circle. Even though it doesn't seem like that's the case, that's actually what's happening, okay? So one misconception is, well, if a car is driven in a circle at a constant speed of 20 miles per hour, then the speed is neither decreasing or increasing. So therefore, there must not be an acceleration. Okay, and that's a misconception that students have. That if you're just going in a circle at a constant speed, you would assume there's no acceleration, right? But remember, acceleration is the change in velocity, which could also just include a directional change. So it doesn't always have to be a numerical value change. It can just be a directional change, and that is what the case is here for circular acceleration. Basically, your direction is constantly changing, so your acceleration is constantly changing, and that's causing your velocity to constantly be changing. That takes care of this video. I will see you guys next time.